Hello, everyone, and welcome to today's webinar. What is machine learning? Will it improve my forecasts? My name is Eric Stellag, and I'll be the moderator today. We're going to begin the webinar shortly, but before we do, let's go over a few logistics. The webinar will run approximately 60 minutes, and we'll save some time at the end for questions and answers. During the webinar, you can submit questions using the control panel on your screen. And you should submit them when you think of them, so they're fresh in your mind. We'll be monitoring the questions that come in, and we'll be covering a certain number of them at the end of the webinar during the Q&A session. We'll try to address as many questions as possible, but if we don't get to your question, don't worry. You'll receive an email follow-up after the conclusion of the webinar. We're also taping this webinar, and we'll email you a link to the video sometime next week. We also will be posting the webinar both on our website, forecastpro.com, under resources, as well as on the YouTube channel. We also have previously recorded webinars that are available in both locations. They're free, and they're a great way to catch up on any of the past webinars that you might have missed. So now, without any further ado, I'm going to turn this over to Sarah Darin, and she is going to explain what machine learning is and how it might be able to improve your forecast.
Thank you, Eric. Hello, everybody. My name is Sarah Darin. My background is in math, lots of math, statistics, and programming, and I have over 20 years of experience working in analytics, working almost entirely with time series data. Most of my career has actually been in consulting. So I've spent many years programming and developing complex custom statistical models for clients, and then working with those clients to help forecast demand for different potential marketing plans and economic scenarios, weather scenarios, things like that. I have had many different roles at BFS, most of them pretty product oriented, a lot with an emphasis on methodology in general. But probably my favorite has been leading the design and implementation of machine learning in Forecast Pro. So this is certainly a topic close to my heart now. And with that, let's start talking about machine learning and what it is. Machine learning and AI have emerged as really transformational methodologies with a multitude of applications, things like facial recognition, medical diagnosing, self-driving cars, market basket analysis, to name a few. But what is machine learning? Machine learning isn't just one approach or method. It really encompasses a wide range of algorithms and approaches. What these algorithms have in common is that they are designed to find and apply patterns. They're learning about the data along the way, so to speak. These methods can be described in two broad categories: unsupervised and supervised machine learning. Unsupervised machine learning uses what we call unlabeled data to find patterns or associations in the data. Unsupervised machine learning is good for things like speech and facial recognition, market segmentation, things where you're trying to put the data into like groups. Supervised machine learning uses labeled data, and it is actually used for prediction. So when you think about where demand forecasting fits into the machine learning realm, it's really going to be within supervised machine learning algorithms. Let's actually take a look at the differences between unsupervised and supervised machine learning and how they work. For example, suppose your data includes images of different fruits, maybe apples and bananas. An unsupervised machine learning algorithm would analyze those images and identify that there are two different types of images, and basically separate the apples from the bananas, but without knowing if each image is an apple or banana, because we haven't told it that this is an apple and this is a banana. So the algorithm is unable to predict if a new image, an unseen image so far, is an apple or a banana. It can simply identify which of these two groups that new image belongs to. In a supervised machine learning algorithm, each image would actually be labeled as an apple or a banana. In this case, we're really calling this whole input data the training data. Instead of just separating the apples from the bananas, the supervised machine learning algorithm would learn how apple images are different from bananas and be able to identify a new image specifically as an apple or a banana. So we send the training data into the machine learning algorithm, we train a model, and then as new data comes in, as test data comes in, new images, we're able to say, this image is a banana and this image is an apple. So again, because we're predicting and forecasting is a type of prediction, it really requires supervised machine learning algorithms. So how do supervised machine learning algorithms work? Let's start by talking about a little terminology. If you hear data scientists talk about machine learning, you're likely to hear them talk about features and labels. Features are like explanatory variables in a regression model. Labels are like the dependent variable. Labels are basically what you're trying to predict or forecast. A machine learning algorithm might be able to automatically create features from an image, and a lot of people try to do that with machine learning algorithms. But more often than not, data scientists actually need to transform the raw input data into organized features. So that's what we're showing here. An example where we've taken those images of bananas and apples and created features that describe those images, that capture a lot of the characteristics of those images. And then we have labels telling the algorithm exactly what each of these images is. So over here we have features, for example, color, length, and shape, describing the images. And then based on those images, we're also able to tell the algorithm what each type of fruit is. This process of organizing the raw input data into features and labels in this case is called feature engineering. Good machine learning models start with good feature engineering, and that means data scientists spend a lot of their time, a majority of their time actually, 60%, cleaning and organizing the data. So essentially doing that feature engineering. So as we embarked on implementing machine learning in Forecast Pro, understanding how we could actually automate feature engineering was really a key part of that research and implementation. If you think about it more broadly, machine learning models have primarily been a tool for data scientists. There are like big teams of data scientists in a lot of companies, and those data scientists are really involved in doing custom coding in Python or R. And they really need a solid understanding of how feature engineering and machine learning works in order to generate these machine learning models. Our goal in implementing machine learning in Forecast Pro was basically to take the need for a data scientist out of the equation. We wanted to give Forecast Pro users the ability to use machine learning models for demand forecasting without having to worry about coding, feature engineering, or model refining. So the automation of feature engineering led us to this key question. What features and labels should we be using in Forecast Pro for demand forecasting? Furthermore, we wanted to make sure that machine learning would work with just the demand history. Most Forecast Pro methodologies require only historic data, and we wanted to make sure that machine learning worked with just historic data too. So what we did was we used the information about the time period and demand from prior periods to forecast demand. And we found that worked pretty well. The idea here is the historic data is the training data, and it's used to create both the features and the labels. In this example, suppose we've read in data from January 2018 to June 2021. The actual demand history is essentially the labels here. So in January 2019, there was 175, let's call it widget sales. But over here, we also have features that are coming from the demand history. Things like sales from a year ago, sales last month. And we can also use information about the time period as features. So we can use what month it is, what year it is. And then all of these features are used to help forecast what the demand was in that actual period. This is the data that we use to train the machine learning model. So basically, the machine learning algorithm analyzes this data to understand how, historically, patterns in these features relate to the current sales. Once you've trained a model with your historic demand, you need to generate forecasts. To do that, you need to provide test data. In this case, the test data is feature values for the forecast horizon. This is actually pretty straightforward for your first forecast period. In this case, we're using data again through June 2021 to, first of all, forecast July 2021. And at this point, we obviously know the month, the year, sales last month in June, and sales last year. And we can use that information. We pass it into the machine learning model that we've trained with the training data, and we can generate a forecast for July 2021. In this case, it's 625, again, widgets. The way you get to 625 going through this algorithm, that can actually vary depending on what algorithm you're using, so what algorithm you've trained. And we'll get into the details if we do it in Forecast Pro in a little bit. But this general scenario of in the first month out, you have all of your feature information and you can use that to forecast. That's pretty consistent across the different machine learning algorithms. Now, once you have this forecast for July 2021, you actually have information to generate features for August 2021 as well. So instead of using actual sales last month for August, you can use the forecasted sales. So you can fill in that 625 and then generate a forecast for August 2021, in this case of 610. And then we can do that again for September. We can put that 610 in for sales last month for September, and then we would end up generating a forecast of 560 for September. Let's actually take a look at how Forecast Pro's implementation works. So what we're looking at here is track version 7. For users out there, you are certainly, hopefully using version 6 right now and not an earlier version. So this might look a little bit different than what you have. And again, machine learning is now implemented in V7. And if you're interested in upgrading to a V7 from your current version, you can expect to be able to do so next month. When we implemented machine learning, first and foremost, we wanted to make sure that machine learning could be used in an automated way, that you didn't need to be data scientists. As I mentioned earlier, we automated feature generation from historic demand. So it is a univariate method. And as an automated univariate method, that meant that it could potentially be included in expert selection. For anyone not familiar with expert selection, that is our AI-driven automatic forecasting algorithm that has really always been the workhorse or brains of Forecast Pro since we came out with the first version 20 or 30 years ago. Essentially, expert selection automatically selects the best forecasting methodology for your data. In order for us to include machine learning in expert selection, we really need to convince ourselves that it would be adding value. Expert selection is a really big part of the identity of Forecast Pro, and making sure that it truly was using the best methodology was kind of a cornerstone that we really need to make sure was maintained. So we did some research, and essentially we determined that machine learning should be used for some data series often enough that it definitely made sense and added value to expert selection. So we did fold automatic machine learning into expert selection. And you will see that when we read in some data. So I am going to go here and select some data. And when I push this read and forecast button here, Forecast Pro is going to automatically use machine learning to forecast all of the series and the data here. And I'm going to exit out here, and let's take a look at the data here. What we're looking at here is the bakery data. So we have cakes and muffins, SKUs, organized by customer. So let's take a look at what models expert selection is choosing once we have machine learning enabled in expert selection. So I'm going to close the override grid here and open up the item report. So what this item report is showing us is for each series that we've read in, we can see what model family expert selection has chosen. And you can see machine learning is coming up a bit here. As we go down, you'll actually see it's actually coming up a little bit more frequently for muffins than for cakes. In order to kind of see some of these machine learning models, what I'm going to do is I'm going to filter and select everything that has machine learning on it. I'm going to add these to my hot list, and then I'm going to close this window and display the forecast report. Okay, so I'm going to go ahead and pick the first end item series here with machine learning. And I'm actually going to go ahead and throw in the fitted so you can see how the model's fitting. So you can see the model's fitting, pretty well historically. The forecast looks pretty reasonable. And if we go down here, you can see that machine learning is winning in our expert selection under this expert analysis here. And it's winning basically because it is forecasting out of sample better than the other contenders that expert selection came up with. As we go down here, we come to the other details of the forecast report. In terms of the model that's being selected, we see some terms about tree depth used, number of trees. We're going to get to that in just a few minutes in the slides. The other thing, though, that you can see here is you can see the features that the machine learning model is using to generate the forecast. So things like seasonal period, interventions. Interventions are things that temporary spikes in the data, level shifts in the data. We see one period lags. What were the sales last month? Seasonal lag. What were the sales last year? And then we also have a 1 year moving average. If we go down to the next item here, we can see some differences in the algorithm. And again, we'll talk about that a little bit later in terms of the model specification. You can see generally the same features coming into play here, but a different order. And we'll talk about why we're ordering them in this way in a little bit as well. One of the things you might have noticed when we read in this data is you saw a dialog pop up and showing the progress in terms of how many series had been forecasted thus far, and it also said machine learning enabled in that dialogue. The reason we have that is machine learning takes longer than other forecasting methods. And that's because machine learning is essentially analyzing the data and creating multiple models to figure out what the best ensemble model, and we'll talk about ensemble models shortly, is. So if longer forecasting times are a concern, you can actually disable machine learning by going to options and going to the performance tab here and checking this exclude machine learning. And I'm going to go ahead and check that now, and just so you can see what can happen. And we're going to reforecast without machine learning. And you can see now we are actually choosing exponential smoothing for this particular series instead. If we do disable machine learning in expert selection, and we certainly, since it does add value to expert selection, we really do recommend that you do use it in expert selection, but we do understand that performance can be a concern. But if you're not using it in expert selection, or even if you are, you also have the ability to use the automatic machine learning models wherever you might see fit. So just like you can assign exponential smoothing with the click of a button, you can assign a machine learning model by just clicking on the icon. So you can see I've now applied a machine learning model to butter cakes, and that is what you can see that the forecast actually did change a bit there, and you can see the details of that butter cakes model there. The other thing that you can do if you do not have machine learning enabled in expert selection, you can actually apply expert selection with machine learning enabled on an item by item basis. So if I go down to carrot cakes here, when we had machine learning enabled, it was choosing machine learning, and here it is not. And what I can do is I can go to the drop down here and I can choose this expert with ML. And what you'll see here is now we do have that same machine learning model being applied. And it's identical to the one when we had machine learning enabled for the project as a whole. Let's actually go back to the slides now so that we can get more details about the Forecast Pro implementation of machine learning. So one of the key things that we needed to think about when we were setting up machine learning was figuring out what supervised machine learning algorithm we should use in Forecast Pro. Setting up features and labels is required for pretty much all supervised machine learning algorithms, but once you have it set up, there are a lot of different algorithms that you could be using with that data. So things like neural networks, deep neural networks, support vector machines, random forests, the list goes on and on. And as you saw, at least suggested in the forecast report, we chose something having to do with trees. We chose to implement extreme gradient boosted regression trees. That's because we wanted to start by implementing a methodology that has been proven to forecast well. And extreme gradient boosted trees have performed very well in recent forecasting competitions, including the M5 competition, the latest of the macrodocus competitions. And those of you who are familiar with the macrodocus competitions know that they're really considered to be essentially the gold standard of forecasting competitions. So the fact that extreme gradient boosting forecasting worked so well in the M5 competition really held a lot of weight with us at BFS. Let's take a look at how a regression tree works with a very simple example. Here we have a very simple tree, and it is using two features. So we have month and we have sales last year. we're generating a forecast value based on the values for these two features. So how do we do that? So suppose we're forecasting August 2021 and sales in August 2020 were 350. We start at the top of the tree. So is the month greater than or equal to 11? In other words, is the month November, December? August is not November, December. So we would go to the right-hand side here and say, no, it's not. And then the next question is, okay, were sales last year greater than or equal to 400? Well, sales were 350. So again, the answer is no. And that means our forecast for August 2021, using this very simple regression tree, would be 300. Let's look at another quick example. So for forecasting September 2021 and sales in September 2020 were 450, again, it's not November or December, so we say no on the first split. Sales last year were 450, and 450 is greater than or equal to 400. So our demand for September 2021 is going to be 550. There are a few other tree terms, let's call them, that you may encounter in the forecast report and our Forecast Pro documentation as well. So first of all, we have split nodes and we have leaf nodes. The split nodes, the ones where we have the features included, are the nodes where you make a decision. The leaf nodes are the ones where you come up with your forecast. Another term that you definitely just saw is tree depth. The tree depth is technically the longest path from the top of the tree to a leaf node. Regression trees are essentially the building blocks for extreme gradient boosting. That's because extreme gradient boosting is what we call an ensemble method. And that means that it takes the average forecast across multiple models. The models that we're averaging are regression trees. Extreme gradient boosting really focuses on finding good, simple trees. And the reason it focuses on simple trees is the goal is to avoid overfitting, and we will actually talk about that in just a minute. If we think back to the data scientist slide and how they spend their time, feature generation was a huge part of it. But another big part is figuring out the right parameters, so tuning the model. For extreme gradient boosted trees, the two most important parameters are maximum tree depth, so how complex each tree can be, and the number of trees, or the number of models that you're averaging across. Using trees that are too complex, too deep, or using too many trees can easily lead to overfitting. Overfitting is something that you really want to avoid. What overfitting means is that your model may fit your data well historically, but it doesn't actually forecast well. The primary goal of a forecasting model is to forecast well, and overfitting can really get in the way of forecasting well. In order to automate extreme gradient boosting, we needed to figure out how to automate the identification of the right tree depth and number of trees to use. The question was, how do we find a tree depth and number of trees that would forecast most accurately? We did that using really a lot of the same techniques that we use in expert selection. So a lot of the same kind of AI-driven technique that powers expert selection really power our automated machine learning algorithm. Let's take a look at how we're doing that for tree depth and the number of trees. So once we've automatically generated features from the historic demand, we use those features to create an initial regression tree for a specific maximum tree depth. We then start adding trees one by one. Once we add a tree, we evaluate the forecast error across those trees that are contributing to the model. We then we ask the question, did adding a tree improve the overall ensemble model accuracy? If the answer to that is yes, that means we're not overfitting yet, and we can add more trees. We would create another tree to add to the ensemble model, evaluate forecast errors across the entire ensemble model, and ask this question again. So we would iterate through this loop until eventually the answer is no, we're not improving the model. And we decide that the machine learning model is now complete. So the general idea is that Forecast Pro's automatic machine learning keeps adding trees until adding trees no longer improves accuracy. Boosting refers to the technique of improving accuracy by adding one model at a time. The extreme gradient part of the name refers to the actual optimization algorithm used to find the next best tree. So now that we know more of the details about Forecast Pro's implementation, let's go back to the forecast report and just take a look at some of these terms again. Okay, so here we are back at in track V7, and again, if we look at the top of the forecast report here, we can see that for this particular example, for the carrot cakes, we were using a maximum tree depth of 2, and we had 15 trees. So the ensemble model included 15 different models. And if we take a look at butter cakes here, where we have applied an automatic machine learning model explicitly, if we go up here a bit, we can see for butter cakes, we actually had a tree depth of 4, and we were using 78 different trees. Depending on what the series is, Forecast Pro's algorithm is going to come up with the best maximum tree depth and the optimal number of trees to use for that series. A few other things that we saw in the forecast report before were feature importance and why we are ordering the features in this particular way. The idea of feature importance is it summarizes how important each of the features is to determining the forecast. Gain, in particular, is focused on how much more accurate each of these individual features is making the forecast model, that ensemble forecast model. Coverage is kind of telling us how relevant each of the features is to forecasting each observation in the series. And frequency is telling us how often the split nodes are representing a given feature. So if we actually look back at the slides very quickly, gain is a percent contribution of each feature to the model's accuracy. That accuracy measure tends to be mean square error. Coverage is the percentage of observations split on the feature. And frequency is the percent of tree nodes that split on the feature. So while automatic forecasting really is a workhorse of the forecasting process, and as you saw when we read in the bakery data, when we had machine learning enabled and expert selection there, expert selection was able to just automatically, with that click of the read and forecast button, generate forecasts. But typically, when you're going through your forecasting process, you're going to start with automatic forecasting, and then you're going to go through and identify which series need more customization. Sometimes customization includes changing the automatic univariate model use or changing to an explicit univariate model. But more frequently, there is simply other information, things like promotions, price changes, stockouts that you want to incorporate into your forecast. One of the strengths of machine learning is that it allows you to include features that incorporate domain knowledge. So that domain knowledge can include things like price changes, the weather, the economy. While Forecast Pro's machine learning algorithm automatically generates features for univariate forecasting, it's not going to be able to automatically generate features to capture your domain knowledge because it simply doesn't have access to your domain knowledge. So in order to integrate your domain knowledge, we have created what we call custom machine learning models. So these custom machine learning models allow you to include things like events and explanatory variables in your machine learning models. And the idea is these events and explanatory variables are a way that you can read in your domain knowledge into Forecast Pro, and then Forecast Pro is able to use them as features in your custom machine learning model. So let's take a look in track V7. So what we're looking at here is mouthwash data. So we have read in our Minty Fresh mouthwash historic data, and this is a data set that is installed with Forecast Pro. We've also read in some event schedules as helpers. And before we take a look at the forecast for this mouthwash data, let's just take a quick look at the data itself. When we look at this 24-ounce bottle of the mouthwash, the thing that really kind of dominates the graph is you have a lot of these spikes happening. Our first spike is actually our first data point, and we see it happening in January. Then we see one in May and October, January again, May again, October, January, July, October. While in the beginning, it seemed like the spikes were almost seasonal, we actually see a shift happening halfway through the data where that May spike seems to have shifted to July. So this is an example where you really want to be thinking about domain knowledge. This is mouthwash. What do we know about mouthwash? Is it seasonal? No, it's mouthwash. The use of mouthwash is probably pretty consistent throughout the year. What is driving these spikes? Understanding that is an important part of the domain knowledge here. It turns out that these spikes are being driven by price specials. So if we look at our event variable here, all of these price specials align pretty well with when these spikes are happening. So this is a case where really to generate a good forecast, we need to account for when these price specials are happening. So I'm actually going to go to my forecast view here. Before we move on to our custom machine learning model, let's take a look at what automatic forecasting is doing here. For the 24-ounce SKU here, you can actually see that machine learning is being selected. And you can see in the forecast here, we're not really seeing the spikes in the forecast period. So the algorithm seems to be learning that they're not really, the spikes aren't being driven by seasonality so much, but we are not accounting for when price specials would be actually happening during the forecast period. If I actually looked at an exponential smoothing model here, you're going to see a lot more spikes here. And that's because the exponential smoothing model is really assuming that the spikes are seasonally driven. And then during the forecast period, these spikes are based on the fact that spikes have occurred in these periods historically. Either way, though, both exponential smoothing and the automatic machine learning algorithm they're both coming up with forecasts which are not good forecasts. They're not appropriately accounting for the domain knowledge about the price specials that really should be integrated into the model. One thing I could do here is I could go ahead and I could do an event model, and that would incorporate the domain knowledge about the price specials when they have occurred historically, and we can see spikes happening, smaller spikes happening when we expect the price specials to occur during 2021. You can also see that the forecast between the spikes is essentially flat. So let's take a look at how machine learning incorporates the events. So to do that, I'm going to go over to the drop down here. I'm going to select Manage. And when I open up this custom machine learning model, you can see that we can name the custom model up here. And then below that, you will see two sections, one for events and one for explanatory variables. You will see all of the events available in your project listed here, and you can select whichever ones you want. If we had explanatory variables read in, they would all be listed over here. And again, you could select as many of those explanatory variables as you might like. On the bottom here, we have automatic checked, and that means that we want Forecast Pro to go into that loop process that we just talked about. You do have the ability to specify those explicitly as well. So for this example, I'm going to go ahead and check price specials only, and I'm going to apply that. And what you'll see is you saw the forecast change a little bit. The actual size of the spikes themselves and the forecast for when these price specials happens is actually really close to the event model one forecast. But what you also see here is, like, in the periods before and after, it's not quite the flat line. In particular, you see this dip happening after the price special in January here. The machine learning algorithm is basically learning that after a price special happens, you are very often seeing a dip in demand right after that price special. And that's pretty common, that if you have a promotion, people are going to move up their purchasing of something, and that causes post-promotional dips in demand. Machine learning algorithm is figuring that out on its own. And you can see here in the forecast report that price specials are actually the most important feature in terms of adding to the model accuracy. Another thing, we mentioned that you can choose as many event schedules or explanatory variables as you want. But another good feature of machine learning is that it's only going to use the variables that really make a difference to the forecast, that should be included in the forecast. This other event schedule I have here, there's one period that has one, so in December 2018, and nothing exceptional happened in that period. So I'm actually calling it a non-event, because this is an event schedule that really shouldn't have an impact on demand for our mouthwash here. So if I go back to our machine learning model, if I add this in, I'm going to move over here. Pay attention to the forecast report, and when I hit apply, you'll see that nothing changed. Essentially, we told the machine learning algorithm to take a look at this schedule one and see if it would make the model more accurate, and it doesn't. So machine learning is not including that in the model. That's great, but there are also some big drawbacks to using machine learning for things like events as well. In particular, when you think about the information that you can get about the impact of price specials, you know that it's an important variable, but you don't know what the impact of price specials is on demand. If we actually switched back to the price specials event model, if we scroll down here, we can see the event code here for price specials. This is a multiplicative adjustment. We can see that when that price special is actually happening, that sales are about 2.2 times higher than when there isn't an event. So we can get information about what the relationship is between the event and demand, and that can be really valuable. let's actually go back to the slides. Okay, so let's take a look at some of the machine learning pros. The first is that it often forecasts noisy and low volume data better than traditional time series methods. When we took a look at the bakery data, I think I mentioned that machine learning was being used a bit more for muffins than it was for cakes. If you looked at the data, you would actually notice that the muffins data is a bit noisier than the cakes data. And that's actually part of the reason why machine learning is being used a bit more there. We've also found that it works for low volume data. For low volume data, often the alternative is going to be a Croston's model, which is non-seasonal. If you have low volume data that has an occasional kind of blip in seasonality, a machine learning model might work well there. Machine learning models also allow you to use key sales drivers via explanatory variables and events. And that's going to be really valuable when you do have domain knowledge that you should be integrating into your model, such as the price specials for mouthwash. It does not require variable selection and specification. Machine learning can do the variable selection for you. And again, you saw that when we tried to include that non-event schedule in the model for mouthwash, and machine learning was able to not select it automatically. It can account for multiple cycles. And this is one that we haven't talked about too much, but things like exponential smoothing, ARIMA, typically work with a single cycle in the data. And by the cycle of the data, we're really talking about, for monthly data, that's going to be what season it is in the year. If you move on to daily data, though, you really now have two different cycles. So you have what day is it in the week, and then you also have what week is it in the year. When machine learning can better handle data that does have those multiple cycles. And it can automatically account for outliers. This is pretty closely related to this first one about forecasting noisy data well too. But if you think back to the forecast reports, we had something called interventions in there. And basically those interventions can identify one-time outliers in the model. That means that you're less likely to see an outlier causing a kind of a ripple effect spike in the forecast period. And it can automatically handle missing data. This is a really nice one because, again, if you think back to the data scientist slide, 60% of the time is spent organizing data and so on. Some of that has sometimes been with handling missing data, imputing missing data as well. So with machine learning, you can have missing data, and the algorithm that we're using will automatically handle that missing data. If you think back to the tree and you have that split node, the algorithm will decide whether, when you have missing data, yes or no is going to be a better suited decision. That said, it's still going to be better to not have the missing data. So while we can handle missing data, ideally it's going to be trained better, forecast better if it has the most accurate data available. Let's talk about some machine learning cons now. First and foremost, machine learning is computationally intensive. So the processing time is considerably longer than traditional time series methods. And again, a big part of that is simply learning takes a little bit of time. Machine learning focuses on forecasting, not explaining relationships. And this is what we were showing you when we took a look at event models versus machine learning with events. The event model was able to capture what the impact of price specials are on demand. If you think about regression, when you have a regression, you have a coefficient that explains what the relationship between changes and explanatory variables have on your demand. You don't get that with machine learning. And because of this is really a consequence of the prior point, it can be hard to understand why a machine learning forecast is what it is. while we can look at a regression tree and understand how you're getting to a forecast, once you have 10, 15, or 200 trees, that relationship of how the feature is really entering into the forecast, the final forecast, is really difficult to understand. Extreme gradient boosted trees do not extrapolate trends currently. So this actually is something that we hope to improve on our next iteration, probably V7.1. But as it is now, and this is true not only in Forecast Pro, but for extreme gradient boosting in general, your forecasts are typically going to be in the range of your historic demand. So if you expect your demand to be very significantly different from your historic demand, extreme gradient boosted trees might not be for you. When should I forecast with machine learning? When you have important demand drivers, when you have domain knowledge that you want to integrate into your forecast, and you don't necessarily want to go through the variable selection process. To clarify this, though, when you have important demand drivers, you shouldn't always use machine learning. There are going to be times that it's going to make a lot more sense to use an event model or a regression model. In particular, if you know what the relationship between an explanatory variable and demand is, instead of waiting for a machine learning algorithm to learn that that variable is important, it often is going to be better just to specify the model that captures what you know the relationship to be. When your goal is to forecast, not explain the relationships between features and demand. When you have frequent unexplainable spikes or complex patterns in your data, machine learning works very well with noisy data. It works very well with outliers and is likely something you should consider if you have very noisy data. When your forecast should fall within the historical range. When you have data with multiple cycles. When, simply put, machine learning outperforms other time series methods. And at first glance, this last one might seem a little silly, but this is a little bit of the reason, or a lot of the reason, why we have machine learning integrated into expert selection. Part of the expert selection algorithm is just simply to figure out when any given algorithm outperforms another time series method. And whatever approach, be it exponential smoothing, be it machine learning, be it ARIMA, be it Crostons, you should use the method that is forecast best out of sample. With that, I'm actually going to turn it back over to Eric for a little bit to take us through a few more slides.
We will be turning to questions and answers shortly, but before we do, I just want to give you a little bit of information. As I mentioned at the beginning, we are recording today's webinar, and we will be posting it both on the website, forecastpro.com, and on our YouTube channel. Also, as I mentioned, there's an archive on forecastpro.com of all previously recorded webinars, and that's a great way to catch up on the ones that you missed. And we'll ship out once everything's up and available for streaming. We'll send you an email to let you know. During the pandemic, we started running virtual workshops, and they proved to be pretty popular. And we have 4 of them scheduled through the end of the year. These are 3-day workshops. They run about 4.5 hours each day. The September 21st through 23rd is a class that's scheduled to be convenient to the Americas. It will be in English. October 5th through 7th will be a Spanish language workshop. October 26th through 28th, we're going to be running a workshop that is scheduled to be convenient for people located in the Asia Pacific region. And then December 7th through 9th, we'll be doing another one for the Americas. And the Americas are also pretty accessible time-wise if you happen in Europe. Also, next year in 2022, we're very pleased to be having our first live event in quite a while, but we have scheduled the Forecast Pro User Conference. It'll be in September. It'll be held in Cambridge, Mass. This is always a fun event, and if you're using Forecast Pro, there's a lot of educational sessions, there's case studies, there's a lot of socializing that goes on, but always a lively conference. It is limited in terms of the number of attendees. We'll be making some announcements about this in the not too distant future, but something to perhaps mark next year's calendar. Okay, the last thing I wanted to mention before we go on to the Q&A is that as Sarah has been showing us throughout, we've been using the Forecast Pro software. As she mentioned, we've been using version 7, which is not quite officially released yet, but will be in August. And if you're interested in learning more about Forecast Pro, we'd love to teach you about it. The easiest and the best way to learn about Forecast Pro is to actually schedule a live demo. And we can even use your data, and we can show you how this all works. So if you are interested in that, feel free to contact us. You can even use the chat function here if you want. But again, if you are interested in learning more about Forecast Pro, the live demo is the way to go. There is also a trial version available on the website. And of course, the website has a great deal of information, including tour videos and things like that. So I encourage you to learn more. And with that, I think we'll be opening this up for questions.
Okay, well, thanks for sticking with us. So we had a couple of last minute changes on how to present the webinar that were due to some changing logistics. You'll notice Sarah's in the office, I am not, and it unfortunately got us off to a little bit of a rough start. So again, thanks for staying with us. I realized we're running a little late on the time, but I thought we would maybe just answer a couple of questions before we sign off. And actually, the question box has been quite busy. And if you have been submitting questions, you do look in the box as well, because we've answered a lot as the webinar was progressing. I'm going to take a couple of questions. Some of these questions were posed early on and then addressed later, so they're a little bit of review. But I'm going to kind of take several questions and put them into a slightly different format for Sarah. Okay, so okay, the first one, we had some questions about what you might call extensions of machine learning. So that, Forecast Pro is currently using this machine learning algorithm on sort of a series by series basis. So we've implemented in an expert selection, and it looks at each individual time series and potentially uses machine learning. As Sarah has shown us, we can also extend that by bringing in explanatory variables and or events variables. But so one question is, what about other applications of machine learning in the arena of forecasting, and specifically the ability to cluster items or to determine groupings, and the ability to perform reconciliation between different aggregated levels of series. So has BFS looked into that and researched that, and any thoughts thereof?
So the short answer is yes, we have looked into it, and it's something on our radar, definitely. I think a real power of machine learning is that ability to transfer learning from one series to another, or to understand how to group things together. So at this point, we are likely to have another iteration, let's call it, of a machine learning. So in the presentation, we talked about how we want to make machine learning work better with trended data, and that's a priority. And another priority is to implement what we would call group ML. And the idea of group ML is that you would be able to select a group node in your hierarchy, and at that group mode, you would actually be applying machine learning to all of the series that compose that node. That said, I believe that question had some questions as well as about machine learning how to group the series together. That is something that we have not really thought about exactly how to implement it, but it's very intriguing. And again, as we move ahead, like, understanding where in the hierarchy we should be forecasting is definitely something that we see ML moving towards, but exactly how the hierarchy is organized, I think we'd have to think a little bit about how that would work, but it's an intriguing thought.
Yeah. I might also mention, a lot of, yes, BFS, the company that produces Forecast Pro, does research and such, but we also follow both the literature and the current research pretty closely. And ML is a relatively new arrival in terms of business forecasting. And there is a lot of ongoing research, both in academia and at certain companies. And I think we're going to see some changes in the methodology and in the application. So we're at the beginning of the machine learning journey, and I suspect there'll be some additional stops that we'll be making as things progress. Okay, let's take one more question, and again, I'm going to kind of combine a few things that have been asked into one, and I'll sort of pose it this way. In the presentation, some people noticed that there was a feature listed on the forecast report that was labeled interventions, and there was kind of a question as to what that does. There was also a question regarding missing data. And as Sarah has mentioned, one advantage of ML is that it handles missing data pretty seamlessly. But the question was asking, is there limitations to how many missing data points there can be? And another one had to do with promotions, and were promotions being handled automatically versus having to bring in an explanatory variable or a helper variable. So again, sort of general comments on the interventions feature, missing data, and promotions.
So the interventions feature is really, it has the ability to select outliers. So we can say this one particular time period, the demand was particularly different from all the others. It can also pick up on shifts. So if there's a shift in the data from, say, 2020 to 2021, then it can pick up a permanent shift. So it really can represent a lot of different things. Technically, if you think about the variable, it actually is just you could think about it as a trend, because it numbers all the periods from 1 until your last period. But within the model, what's really happening is it's looking at, okay, is a particular period different? So when you have that trend variable in there, with the way regression trees work and the way you split on variables, it ends up having that dual function of outlier detection and or outlier correction, really, and level shifts. And okay, the second part of that was
I made it difficult by throwing a 3-part question at Sarah, so we'll take some pity on her. So the second question was missing data, and basically any special things that we have to do when we have missing data, and or any guidance in terms of if I've got too much missing data, are there issues?
Right. So from a technical standpoint, XGBoost itself will handle any amount of missing data. And the way that works is that missing, when you're going through the tree, if there's a missing value, it will come up with a rule for when you have a missing value on that variable. So from a technical standpoint, that's how it's built into the algorithm. That said, and I think I said this in the presentation, you don't want to have a lot of missing data. So in order for machine learning to really work well, And to learn from your historic data, things need to be pretty well represented. So it's nice that you don't have to go through that imputing. But in terms of a threshold, there isn't a precise number, but if you can avoid missing data, do so. But on the other hand, machine learning will be a little bit more robust. Instead of just excluding an entire time period because of missing data, it will use the information that is available for that time period. So that's good. But that doesn't mean that you shouldn't try to fill it in if you have the ability to do so.
Okay, and then the final third of the trifecta is promotions, and the concept of is handling the impact of promotions automatic, or do we need to be bringing in information about the promotions and pros and cons thereof?
Gotcha. Okay, so this is one where if you're not bringing in information about the promotion, so like when the promotions happened, either through an event variable or an explanatory variable, machine learning would be able to detect that something different was in that period. And that really will be happening with this interventions feature that we include. So we'd be able to see that there was a spike and say, it doesn't look like this is following a seasonal pattern. So we're going to say this is a one-time thing. When you're thinking about promotions, though, that's not really what you want. You want to know when promotions happened historically and when they're going to happen in the future. So while machine learning will be able to kind of control for promotions in your historic data, in order to really incorporate promotions into your forecast horizon, you really need to be including that domain knowledge as a event or explanatory variable.
Okay. Well, again, I want to thank everyone for taking some time out of their day to join us and learn a bit about machine learning. I hope you've found it useful, and thanks for bearing with us as we've battled the technical difficulties that we encountered. As we mentioned previously, this is a quarterly webinar series, and we do have another one coming up, which we'd encourage you to sign up, and hopefully we'll see you at a future one sometime soon. So thanks again, and take care.